7.2, inverses of relations and functions. So you have seen the word inverse used in a lot of ways. And I've used the word inverse, like inverse operation. The additive inverse of 3. What can we add to 3 to get it to cancel? -3. What is the multiplicative inverse of 5? 1/5. So the additive inverse is we add two things, it cancels to 0. The multiplicative inverse, 5 times 1/5, it multiplies to 1. You can also find and apply inverse to relations and functions to graph an inverse function. So see this line, y equals x? That's how we reflect inverses. So if you look at a graph, the line y equals x should not be tricky. It's y equals 1x plus 0. So if you would think about putting your point there at the origin, you go up 1 over 1, you would get this line. Now, this is a line of reflection. So if I'm talking about an inverse point, if my point is 1, 4, that's the original point, its inverse is going to reflect over this line, and the inverse becomes 4, 1. So what happens when we find an inverse of a point? We just flip the x and y. So if you're reflecting something over the line y equals x, its inverse, xy, is now yx. Okay, so this is your line of reflection. Got it? That's an inverse. So it's equivalent to switching the x and y values and the ordered pair, what I just talked about. And that's exactly what inverses are based on, is switching that x and y. Okay, a relation is a set of ordered pairs. So everything that I give you is a relation. But if it's a function, every x value has exactly one y value. Remember the definition of a function. Then we're going to start talking about inverse functions. Okay, so remember, if it's a function, that quick definition is every x has exactly one y. The other way to test if something is a function, remember the vertical line test? If a vertical line goes through and it hits no more than 1 point, then it is a function. All right, so we have a function here. Every x has exactly one y, and we're going to graph it. Now it says graph the ordered pairs and connect them. So if I didn't tell you connect them, this would be just a discrete graph of just ordered pairs, 5 ordered pairs, but I'm telling you to connect them. So take a second and graph this. 0, 2, 1, 4, 2, 5, 4, 6, and jumps to 7, 8. All right, connect them. No arrows. We're just connecting the points. I feel like I graphed something wrong. 4, 6, 7. What did I screw up? Oh, that's what I should have. No, I skipped 3. I just don't feel like that got in the right spot. We'll just make it a little thicker. All right, so there's just like a slight curve to it. We've got the points there. Now, we want to graph the inverse on the same graph. Okay, finding the inverse is just flipping the x's and y's.
It's 8, 7, not 7, 8.
Oh, that's where I messed up. Okay, it should have been 8, 7 right here.
Yeah.
I knew something looked weird. Okay, ignore that. This is what it should be. Okay, to find the inverse, we are just flipping. So 0, 2 becomes 2, 0. 1, 4 becomes 4, 1, 2, 5, 5, 2. 4, 6, 6, 4, and 8, 7 becomes 7, 8. So every x and y get flipped. Now take a second and graph the inverse. No, you don't have to, but if you have another color and it helps you, you can.
Will these always intersect?
They will intersect over that line of reflection, but if they're on opposite sides, they might not like cross each other. So if I graph this, and I actually do it right this time, 2, 0, 4, 1, 5, 2, 6, 4. I feel like I screwed up again, guys. 2, 0, 4, 1, 5, 2. Jeez. 6, 4. And then 7, 8. There we go. connect those. And this is where I want you to see that line of reflection. So if you take a second and you look at this line y equals x, which would be 1, 1, 2, 2, 3, 3, that's your line y equals x. That's your line of reflection. And so to me, it's much easier to make a chart and then flip the chart and then graph those points than say, oh, let me graph this and fold it over here. So if my graph crosses over this line of symmetry, then the points will intersect. They'll only intersect on that line of symmetry there, like that. But if I just had something over here, it would just reflect over here. They might not cross. Okay, now let's talk about the domain and the range. On the original graph that I have in red, the domain, okay, there's no arrows on here. We started at the point 0, 2, and we finish at the point 8, 7. So the lowest x value for the domain is 0, and that is included. And as we go across the graph, the highest x value is here at positive 8, and it is included. So there's no arrows, it just said to connect the points. So that's why it's continuous. If it didn't say connect the points, we would have just listed 0, 1, 2, 4, and 8. Remember those discrete ones. All right, what is the range of the original graph? Well, the lowest point in my red graph is 2, and the highest point is at 7. So 2 to 7. There's my domain and range of the original. Now think about its inverse. If you really think about it, we switched x and y. So my range is now 2 to 7. Look, you started at 2 for x and you ended at 7. My range is the old domain of 0 to 8 because I start at 0 and I go to 8. So when you switch x and y, you can see that your old domain becomes your new range and vice versa. Okay? Are we good there?
Ready. How does it?
Talk about it as a function. When a relation is also a function, you can write the inverse function f of x as f to negative 1 of x. So that's new. We know f of x is the same as y equals. And so instead of having just two functions, here's my original function f of x, and f to the negative 1 of x is the inverse function. This notation does not indicate an exponent. So a negative exponent, moves it down. So like a to the negative n is 1 over a to the n. This is just notation. I have the original and I have its inverse. So functions that undo each other are called inverse functions. Like the inverse of multiplication is division. The inverse of addition. What's the inverse of squaring something? Square rooting it. Yep. Okay, so if you look at this idea, it's a little bit hard to see on here. We have an input of 3, and the function is x plus 6. So if we do 3 plus 6, we get an output of 9. Okay, now take that 9 and put it in the function's inverse. 9 minus 6 is 3. So see how we started with the 3 and we ended with the 3. If functions are inverses, they cancel each other out. So we'll get more into that later, but we're going to find the inverse. So first things first, I'm giving you the original function. F of x is 3x plus 6. What kind of function is this? What would it graph? It's going to graph a line. Now, if I want to find the inverse, the first thing I'm going to do is I'm going to rewrite this as y equals 3x plus 6. To find the inverse, the first step is to switch x and y. So it's now going to be x equals 3y plus 6. So just like we flip the order pairs, we're going to flip x and y. Then the second step is going to be to solve for y. So we flip the x and y, and then we solve for y. So what's the first thing you do when you solve for y? Yep, subtract that 6. So x minus 6 equals 3y. And then what? I'm going to divide by 3. I want to get rid of it. Now, instead of dividing the whole thing by 3, I'm going to break it up and divide each piece by 3. And I'm going to say that I have 1/3 x, not 3x, 1/3 x minus 2 equals y. That's a big mistake. we see x divided by 3, write 3x, but there's a 1 there. All right, the third step is to write it in function notation. Function notation. So now we have f to the negative 1 of x. So we started with f of x. That is the original function. And now I'm denoting this is the inverse, which is 1/3 x minus 2. So 3 steps to finding inverses. Switch x and y, solve for y, and then rewrite it in function notation. Okay, so now we're going to graph this. I'm going to graph the original one here in this ink. F of x equals 3x plus 6. I'm going to use my slope and y-intercept. My slope is 3 over 1, and what's my y-intercept? 6. So on the y-axis, put a point at 6. I'm going to go up 1, 2, 3, positive 1. I'm going to go down 1, 2, 3, negative 1. All right, so sketch in your line. And the reason we're going to connect these is x can be anything. So we can connect it, graph that line. Then we're going to graph its inverse function. So we are going to graph f of negative 1, x, equals 1/3 x minus 2. Okay, and so just to remind you, the slope is 1/3. The y-intercept is negative 2. All right, so I'm starting at negative 2. I'm going to go up 1 and right 3, up 1 and right 3. I can go down 1 and left 3. There's my line. And where's that line of symmetry or axis of symmetry? Well, it should go right through here. That axis of symmetry is at 1, 1, 2, 2. Hopefully I have this line. Probably should just do it by hand. There is my axis of symmetry. This is the line y equals x. So do you see how that reflects and how it intersects right in that point there?
Is our line all for axis of symmetry? Is it always y equals x, or can we do a ratio?
So we're going to do the same thing. We are starting off with a function. I would like you to find the inverse, put your final answer in function notation. Now, one of the things you're going to do is some people are going to look at this and say, oh, well, if it's subtraction, I'll add 5, and if it's division, I'll multiply by 4. But if you write 4x plus 5, you're going to get it wrong because of the order of operations. So first step is going to switch x and y. If it helps you to see this, rewrite it, but you could skip right to x equals y over 4 minus 5. So let's solve this for y. So first step, switch x and y. Second step, solve by adding 5. And I've got x plus 5 equals y over 4. Now, how do you get rid of that y divided by 4? Multiply by 4. And this is the key. When you multiply by 4, you have to multiply everything by 4. So that's where people will sort of mess up with the order of operation idea. We should get 4x plus 20 equals y. So the inverse, f of negative 1 of x, is 4x plus 20. It's not mathematically challenging. I mean, some can be depending on what you're given. But what I want to point out is, again, some people look and say, okay, it's going to be adding 5 and multiplying by 4. There's your multiplying by 4, but you had to multiply everything. So I want you to switch x and y and then do the inverse operations to solve it. Okay, so you try example B here. Find the inverse of this. All right, now, if you looked at this as y equals and you want to distribute that, you can. You could have dealt with it without distributing. That's supposed to be a 1. So first thing I'm going to do is I'm going to switch my x and my y. And then I'm going to start solving by adding 21. And I get x plus 21 equals 3y. And then dividing everything by 3. And you could show the answer like this. So someone might have f of negative 1. F to the negative 1 of x equals x plus 21 over 3. Or I typically break it up and I'd have it like 1/3 x plus 7. So either of these answers are acceptable. So you could have either one. You don't need both. But I do want to talk about one other thing real quick. You could have solved this without distributing that 3. You could have said, hey, I'm just going to jump into it. If you did that, you would have divided by 3 first and got that 1/3 x equals y minus 7, and then you would have added 7. And you see I get that 1/3 x plus 7 that way. Okay, so 2 ways of doing it. It's up to you as long as you're getting the right answers, and either answer is acceptable. Okay, vertical and horizontal line test. You already know the vertical test. The vertical line test helps you determine if the given graph is a function. So the idea is if the x doesn't repeat, that means every x has exactly one y. So if I'm doing the function f of x and I do the vertical line test, it fails it, right? So f of x is not a function. The original one is not a function. It fails a vertical line test. Now look at this one. Does it pass or fail the vertical line test? So the first one, f of x, the original function, it is a function. Okay, our third graph, does it pass or fail the vertical line test? It fails the vertical line test, so it is not a function. So you should be able to tell me function or not a function and justify it with your vertical line test. Remember, this vertical line at x equals 1, x equal 1 has a point at 1 and a point at -1. So that x has more than 1 point. Same thing here. We have a point at 4, 3 and 4, 5. Now, tell me if its inverse is a function. So if you look at this, the horizontal line test, or the HLT, can help determine whether the inverse is a function. So you know how when we find an inverse, we flip the x and y? So instead of flipping the graph and regraphing it, I'm going to flip the test. So is its inverse, we're still doing these, is its inverse a function? Does it pass the horizontal line test? Yes. So its inverse is a function. It passes the horizontal line test. Then is this inverse a function? No, because it hits 2 points here, right? So the inverse is not a function. Okay, why is it not a function? It fails the horizontal line test. So if you think about it, this point right here is at -2, and we'll just say like -2.75. I'm just making that up. It's close. And this point is at -2 and maybe -0.5. Okay. I just screwed it up. I'm backwards, guys. Sorry. -2.75 and then -2. I know. And -0.5 and -2. Okay, so here's the deal. I was going backwards. The original point, every x has exactly one y. But if I flip the point and make the inverse, then it doesn't, because the y value has more than one x. And so this would be like the inverse function here, and this would be like the original function. So this x on the inverse would have more than one y. Okay, so does this pass or fail the horizontal line test? It passes, so it is a function. So the first point I gave you was if I flipped x and y. All right, vertical line test tells us if the graph we're looking at is a function. Horizontal line test tells us if its inverse is or is not a function. All right, so looking at this, the horizontal line test is telling us if its inverse is a function. So this one is a function. This one hits more than 1 point horizontally, so it is not a function. All right, so why does that work? The vertical line test is testing for x values that repeat. The horizontal line test is testing for what? Y values that repeat. The horizontal line test is looking for repeated x value or y values. So if you think about it, repeated y values, so repeated y values would be repeating x values and its inverse. Okay, So the horizontal line test is looking for repeated y values. Repeated y values, I don't know why I wrote that. Repeated y values, sorry, I skipped that. Repeated y values would be repeating x values in the inverse. So if we look at these functions down below, they're the same, almost the same functions, are they? Yeah, so except for number 3 is different. So this one passes. The original we said fails. So the original is not a function, but its inverse is a function because it passes the horizontal line test. We determined that this one, the original, is a function, passes the vertical line test, but its inverse, we determined, is not a function. Okay, now the last one to change. Is the original a function? How do I know? It passes the vertical line test. Is its inverse a function? No, because it does what? Fails what? Yes. So, one more time. A vertical line test tests the graph you're looking at. Instead of flipping the graph, we flip the test. So here is a perfect example. The original graph is a function, and if I flip this graph, this is its inverse. This is not a function, and that's why its inverse is not a function.